Hello everyone, welcome. Today we will see chapter 4 single factor experimental designs and their analysis of variance, which is ANOVA. So based on this, just after the end of this chapter, you will be able to explain what single factor experiments mean, and you will identify the appropriate designs for single factor experiments, and also you will identify the ANOVA procedure for single factor experiments, and also you will identify the components and the skeleton of ANOVA table or ANOVA layout, and then finally you will be able to identify the basic concepts of each single factor experiment. So when I come to the introduction, just a single factor experiment, SFE, is an experiment in which only single factor varies while the other factors keeping constant. So one factor varies or has different levels where the others are constant or uniform, no variations at all. That means in such experiments the treatment consists of solely of the different levels of a single factor or variable factor. That means, for example, we can mention that the variety trials, which different varieties considered as treatments, and those the varieties or the different number of varieties considered as levels or the treatments in the other on the other factors are constant. That means keeping constant. And also we can mention the other example, the fertilizer trial, in which several rates of single fertilizer, or it may be nitrogenous fertilizer, from 0 up to, you can take several levels above, and all the other factors should be constant. In such case, in such case, just we can say that the experiment is single factor experiment. So different types of designs can be used for such kind of experiments, but the most commonly used designs are a complete randomized design and randomized complete block design, Latin square design, lattice, and augmented designs. So the almost 5 experimental designs are most commonly used for single factor experiments. So generally, we can categorize the experimental designs into 2: complete block designs and incomplete block designs. In most of the experiments, the available experimental units, the materials, and all associated factors need to be classified the experimental designs into 2. That means, so when the available experimental units are grouped into blocks having more or less identical characteristics, to remove the blocking effect from the experimental, such designs termed to be block designs, because we have created some homogeneous groups to remove the blocking effect, or so what the known source of variations. And when all treatments and each treatment in a block is randomly allocated or assigned, and it is all the treatments with full replication, and the design is called complete block designs. In the case of this complete block designs, all the treatments should be present in each block, and each treatment should be replicated equally. That means, whereas in other case, the number of treatments is too large. When the treatments become too large, and the full replication in that case may be difficult, and also obtaining homogeneous environments for the larger number of treatments could be difficult also. So in such case, just we will use incomplete block designs. That means the blocks do not have or contain a full replicate of the treatments. It means each replication, or each block will not contain all the treatments. In other case, that means, so in such case, such experimental designs with blocks containing an incomplete replications of the treatments termed to be incomplete block designs. So when we come to the first design, which are commonly used in the laboratory or in the greenhouse, or in general in homogeneous environmental conditions, just we can see that's completely randomized design, or CRD. This is a design where the treatments are assigned completed at random. There is no restriction of the treatments assigned or random. There is no restriction. There is no restriction of the randomization of the treatment to the experimentality. That means, so each experimentality will receive equal chance of any treatment. That means, so completely randomized design is only appropriate for experiments with homogeneous experimentalities, such as for laboratory or another case in the greenhouse, where the environmental effects are relatively easy to control. But in the field experiments where the variation is higher, CRD is not often used. So the CRD is flexible and the statistical is also simple, even where the unequal replications or when one observation or treatment is missed from the total observation. So in such case, the analysis and the method for CRDs becomes simple. When we see the model for CRD to express the relation between the response variable and the treatment or the factor and the effect of other factors unaccounted for is just, we can see here the model why the dependent variable, it might be planted yield in the other, or the dependent variable is what the effect or the function of population mean, treatment effect and the error effect. That means, when we come to the advantages of this design, it's flexible. Just we can use different number of replications. That means, just one treatment may be replicated 3 times, in the other treatments may 4 times. So we can use different number of replications. And also simple analysis, just with missing values. Just if one observation is missed from our observation, just we can estimate the values with what's missing with missing data, with no restriction. And also less of information due to missing data is very small, because the environment in the where the design is implemented is less or higher, uniform. It's also the simplest and the least restrictive design, because as I told you earlier that its mathematical or the ANOVA procedure is simple, and also no restriction of randomizations. That means, and it provides maximum degree of freedom for the error term and the precision for each precision or error estimate is more reliable, because if we can mention that one example in an experimental with 4 treatments and 4 applications, the error for CRD, that means T into R minus 1 is the experimental error degree of freedom for CRD, whereas the T into minus 1 and R minus 1 is for RCBD. So you can submit the values, treatment and applications for each formula, and then you can obtain that the value for error term 12 and error term 9. So in such cases, the error degree of freedom for CRD is larger than that of error degree of freedom for RCBD. Because of this, the precision becomes larger, while we calculate mathematically from the ANOVA procedure, just this degree of error degree value is very nice, and also important to calculate the mean square values, and that mean square values also very important for calculating or estimating for F calculated or F values. In such case, the higher values are very indicative for the more reliable of the experiment. That means, when we come to the disadvantages, its precision is less when experimentals are uniform. Means, if our experimentalities are not homogeneous, this what the CRD is not, that means implemented or used, and also the precision becomes lower if we use that design. Whereas it's inefficient because randomization is not restricted, because randomization and blocking are very important in what estimating the or minimizing the error. That means doesn't take that means the advantage of blocking. So due to this, the block is the design is not efficient. That means when we come to the randomization, the layout of CRD, randomization is not restricted because all all treatments are at a time randomized or assigned at random in all the experimental units. That means there is no blocking at this time. That means so randomization is not restricted, and we can use also lottery method or table of random numbers. For example, assume a given experiment is to be conducted using 6 treatments in 5 replications. Just we may have what 30 total experimental units, because you can multiply, and to obtain this amount you can multiply your replication and also treatments. So to see this, the step-by-step procedure for randomization and the layout of CRD are given as follows. This for a greenhouse experiments having A, B, C, D, E, and F treatments and replicate 5 times those. So we have what 6 treatments. 6 treatments, and also each of them are replicated 5 times. That means so the first step could be determining the total number of experimental plots or experimental units, and also the number of treatments T and the number of replications T. R. To obtain, as I told you earlier in the previous step, we can obtain that the total experimental units by multiplying the number of replications by number of treatments. So if we multiply this, just we will have 30 experimental units, and we can assign this experimental unit, just assign the plot number to each experimental plot in any convenient matter from 1 up to 30. We have 30 plots, and also we can give a number, that means random numbers, or we can use consecutive numbers from 1 up to 30. Then assign the treatments to the experimental units randomly. We have 30 plots, and also we have to assign every treatment with its replication to all